Hello, it's Scott Manley here. I've talked a lot about fuels in the past, usually for rockets, but today I want to go into detail on fuel for piston engines, which is still a subject full of chemistry, physics, and engineering. It's just not rocket science. But I want to look at a very specific problem that most people these days don't even know is still relevant. In California, last month, the first public sale of unleaded aviation fuel happened, and this is specifically at Reed Hillview Airport down in San Jose. The local county had passed a law that had stopped the sales of leaded aviation fuel, and a new lead-free fuel now enabled them to reintroduce the 100 octane fuel sales. Now, granted, these local laws are more likely because the city would really like to shut down that airfield so that they can sell the land to property developers, but more importantly, it might surprise many of you out there to hear that there's lots of aviation fuel still containing lead. You probably thought that was all eliminated in the 1980s because lead is pretty damn toxic, right? Well, this specifically is only for piston engine aircraft, using small engines similar to car engines, but not really nearly as modern, right? This doesn't include jet engines or turboprops. These run on something called Jet A, and it represents the vast majority of aviation fuel that's being burned. So don't worry about lead poisoning from airliners or chemtrails or anything. There are also a few diesel piston engines for aircraft that can run on Jet A, but those engines tend to have to be heavier because they need to be stronger for the higher pressures. So anyway, the majority of small piston engine propeller planes run on a type of fuel called 100 low lead. That's 100 octane low lead, right? It's also known as avgas generally. And when I say low lead, by the way, I mean it's about 0.56 grams per liter or 2 grams per US gallon, but who would use those ridiculous units? It's dyed a beautiful shade of blue to help identify it, but at a chemical level, it's not nearly so beautiful because of all that lead in there. Now, car fuels at the pumps that we see, they're more likely to be at best 90 octane. And my little plane that I have, it happily runs on that stuff. But the Cirrus that I rent for my IFR training, that's supposed to run on the 100 octane fuel, and it could be damaged by running on low octane fuel. Now, a lot of people out there have heard about high octane gasoline, right? Or high octane petrol, but they don't actually understand what it means. People associate high octane with high performance cars, and they think it's something about the energy content. You know, some chemistry nerds like myself in high school, we heard the word octane and thought, oh, that must be all about the molecule octane, which is a hydrocarbon. It's an alkane, which is often shown as a chain of 8 carbon atoms, oct, right, with hydrogen atoms all around the edges. So the 8 times 2, 16 plus 2 more for the end, you get 18. So 8 carbon, 18 hydrogen, that is octane. So I thought I was a pretty smart kid for realizing that and making that link until I realized that I had it all wrong just in the last year. Now, from an engineering perspective, the octane rating is about making the fuel burn smoothly inside the engine. In the early days of engines, there was this mysterious problem known as knock. Under some conditions, the sound of the running engine would change and it would frequently cause damage to the engine. Right? The knocking was when the mix of the fuel and the air in the cylinder would burn so quickly it would detonate. That is, when the spark ignites and in the mixture a flame front moves through the fuel mixture and it can accelerate to the speed of sound, and that way when it arrives at the piston heads it generates a shock wave which damages the piston. So that is what detonation is, or knock. A big contributing factor to detonation is the physical conditions inside the engine, like the mixture ratio, the compression ratio, and other factors. Compression ratio is important because raising the amount of compression inside a piston engine increases the power available and the efficiency. So it's desirable, but increasing the compression too much raises the chance of detonation. The fuel and the air molecules get closer to each other, making it easier for the combustion energy to bounce from one molecule to the next and go through the engine and pick up speed. Anyway, another problem was that different sources of fuel could have different behavior. So a fuel from an oil field in California could be just fine, while a fuel from Texas oil fields might be a disaster waiting to happen. Gasoline comes out of refining crude oil, and it's largely fractionated out. It's based on the boiling point and the freezing point of material of the molecules. So it's a collection of many different hydrocarbon molecules that all boil at roughly the same range of temperatures. Gasoline actually needs to boil in the right temperature range so that it can be used in carburetors, be injected into the cylinder, and evaporate before the combustion happens. Prior to the invention of the internal combustion engine, by the way, there wasn't a lot of demand for these really light, volatile distillates. The oil producers were primarily making kerosene for things like lanterns. And the volatile light fuels, they were just burned off at source since they were pretty much useless at the time. Obviously, the world has changed a lot since then. Anyway, because the fuels came from different oil fields, the actual makeup of the fuels with these similar boiling points could be hugely different in terms of the molecules and isomers and everything. So some fuels would have higher detonation probabilities than others. The engine makers and the fuel refiners would both refer to this, by the way, as the fuel problem, while they both insisted it was the other party that was responsible for fixing it. And eventually, industries and the government worked together to find ways to understand the fuel detonation and came up with ways to standardize the performance of a fuel so it could work across the US and ultimately across the world. So one approach was to run test engines on pure hydrocarbons containing one specific molecule, and the standard that emerged was using N-heptane as the 0 point on the octane scale and isooctane to represent the 100 point on the scale. Now, remember how I made the connection between octane, the molecule, and the octane rating? Well, this is true. It is a specific isomer of octane that calibrates the scale. It's 2,2,4-trimethylpentane. So that's a chain of 5 carbons with 3 methyl groups hanging off the side at the 2 and the 4 position. These were chosen because the pure versions could be created for testing. The heptane could apparently be refined from the sap of Jeffrey's pines, and trimethylpentane could be made by reacting butyl alcohols. So that beautiful single chain of 8 carbon atoms known as N-octane, the molecular format that sort of jumped off the page and into the forefront of my mind every time I saw octane written on fuel pumps, that actually has an octane rating, which is negative, means it's worse than 0 octane because it's so prone to detonation. And if you think about this, it kind of makes sense from a structural perspective that the long, thin molecule with a high surface area was faster and easier to break up during combustion than the more compact branching molecule that has a lower surface area. And you might naively think that if it's slower burning, then it must have lower energy. But actually, if you compare the energy from the straight chain of N-octane and the branched isooctane, there's actually 7% more energy in the more stable, slower burning molecule. So, it's not giving up energy, it's just making it burn more slowly. So anyway, armed with those 2 standard molecules that could be produced purely, the researchers could mix them to create, say, an 80-octane reference fuel with 80% isooctane and 20% N-heptane. Then they could run that on a test engine where they could adjust the compression ratio, they could figure out where it would run fine and where it would start to detonate. And so you would have then a standard performance envelope for 80-octane fuel. So then you could take fuel from one provider that had been refined, you could run it through a similar set of engine tests, find out where it detonated, and then figure out what its octane number was. So now you would have a specific quantifiable measure showing just how much better fuel from California was versus the fuel from Texas. And the people making low-octane fuel were, at that point, understandably interested in ways to raise their octane number of their fuels. And there were a number of octane-raising additives that were investigated and developed. Things like alcohols and benzene work pretty well. Toluene at one point was a leading candidate too, because after World War I, there was a lot of excess toluene available since you used toluene to make trinitrotoluene, which is TNT. So you could take the low quality fuel, add say 20% benzol to it and make a usable fuel. But the real king of the additives was tetraethyl lead. That is a lead atom with 4 ethyl groups hanging off the sides. And adding small amounts of that, parts per thousand, would work wonders on making the fuel knock resistant. Sure, everyone knew that lead was hella toxic, but it was insanely convenient, especially for pilots who would be able to carry a gallon of tetraethyl lead in their plane. And when they got to whatever field that we're at, they would just mix it with the local fuel to make sure that it was sufficiently high octane and then continue on. They didn't have to worry about the local sources. But, there was one, infamous case where Jimmy Doolittle, his plane, they spilled the tetraethyl lead in flight and he ended up being hospitalized because of the toxic lead. There wasn't much talk about this toxicity, by the way. The primary supplier of tetraethyl lead branded itself as the ethyl company, carefully avoiding any mention of lead that they were adding to the fuel. Incidentally, another name that was involved in the development of aviation fuel and lead in aviation fuel is a guy called Edwin Aldrin Sr., Buzz Aldrin's dad. So yeah, World War II, and that meant that there was suddenly a huge incentive to push the performance of aircraft to gain an advantage in the skies. It turned out that the Luftwaffe used fuels which were about 90 octane, while Allied aircraft were running on 150 octane fuel. And this difference is largely because much of the fuel production in Germany started using coal, and they could make the hydrocarbons from it by reacting it with hydrogen in a pressure vessel with heat, and out would come a mixture of hydrocarbons that they could turn into aviation fuel or gasoline or whatever, right? The Allies, of course, they could just get it out of the ground and they could use the best fuel for the aircraft that they needed it, and they could add the lead to raise the octane to what was needed. To be competitive in the skies, the German aircraft designers had to come up with some new tricks. They used a combination of larger engine displacement and engine systems that could inject water or alcohol mixtures. Of course, the flip side of this was that German engineers were forced to develop direct fuel injection before the Allies, who were still messing around with carburetors. And it also made them more interested in jet engines because the continuous nature of the combustion process meant that there wasn't really a detonation problem with jet engines. So now, fast forward to the 1970s, and pollution from cars is having real effects on the citizens of the world. It isn't just lead pollution initially. There's a whole lot of secondary combustion products that are making smog. They massively reduced the air qualities and led to medical issues. And one technology to reduce these secondary products was something called the catalytic converter. But one problem with that was that lead in the fuel would poison the catalyst over time. And while they were beginning to develop catalysts that would be unaffected by the lead, that process would kind of be irrelevant once they were decided that lead was actually one of the primary pollutants and it too needed to be eliminated. So in the 1980s, cars start switching over to unleaded fuels. Millions of cars on the road get replaced. And so it's a massive positive for society. All that lead had been slowly poisoning people. People like me that pretty much grew up around it. It probably made them dumber and reduced their self-control, and it probably peaked in the 1980s, which explains a lot of 80s fashion. But aircraft, they actually got an exemption. While the cars had to change over, the aircraft were allowed to continue, and they weren't even given a deadline on when aircraft were supposed to sunset lead in the fuel. The reason why aircraft got allowed to continue, there was a combination of factors. Firstly, it was a small part of the problem. There wasn't that many planes compared to all the cars on the road. And so that was, planes were not a low-hanging fruit at the time. Secondly, aircraft with their required annual inspection and maintenance rules and limitations on modifications meant that aircraft lifetimes were many times longer than cars. There's aircraft from the 1940s that are still operating at my local airfield. And finally, design issues peculiar to aircraft engines increase the need for high octane fuels. So if you look at one of my cars, I have an aging minivan which works great. It has a 3.6 litre engine and it generates 260 horsepower. But that Cirrus that I fly that's like $500,000, that has an Lycobing IO 390 engine which generates 215 horsepower from 390 cubic inches, or 6.4 litres. That's almost twice the displacement for less horsepower. The difference here is that the aircraft's engine is limited to 2,700 RPM, while the car engine can go much higher. There's a gearbox in the car that converts that high RPM and translates the engine speed down to the lower speed of the wheels. So the engine can be running at 5,000 RPM to generate peak power, but on the plane, the propeller is linked directly to the shaft. And the prop rotation speed is limited because the prop tips, if they get too fast, they start to approach the speed of sound, and the engine becomes much better at making noise than it does at making thrust. So plane engines with the prop directly on the shaft, they have to run at lower speeds, and they can only get more power from increasing the displacement or increasing the compression ratio. And so they were built expecting to operate with 100 octane gas and high compression ratios. The engines are also old, and they have old, dumb, but reliable engine ignition systems that can't adjust the timing of the spark or other stuff that modern car engines can do. Now, another interesting point is the small plane I own. It uses a Rotax engine, and that engine incorporates a gearbox between the engine block and the propeller. So the engine runs at over 5,000 RPM, and the prop is running about 2,800 RPM. And that means that the little engine can generate 100 horsepower from a 1.4 litre displacement. And it'll also run on 90 octane car gasoline. So it's unleaded. And this is a not entirely convenient process, to be honest, because if I want to get unleaded car fuel, I have to drive to the local gas station with a bunch of 5-gallon gas cans in the back of my car and fill those up individually. And it's funny because sometimes I'll drive over there in my little electric car and load up with more fuel than the monster truck sitting at the next pump. Anyway, about 60% of old aircraft engines don't actually need the 100 octane. They could get away with something lower, like 90 octane. And that works well enough. But the problem with car gas is that there's rules in the US that encourage adding ethanol. And this is partly a government incentive to farmers that will take the corn they harvest and turn it into alcohol in the fuel. But the ethanol also adds octane to the fuel, and it's also an octane booster. So there's other advantages. But the downside of the ethanol is that there's all sorts of things that ethanol will attack, like plastic or rubber components. And older fuel systems in old aircraft, vintage aircraft, may not be compatible with this stuff. So there is a specific type of ethanol-free gasoline, which we call MOGAS, and it can be found at a limited number of airfields. And I hear it's actually common for certain classic car owners to arrange access to the MOGAS at airfields, since they don't want ethanol. It doesn't care whether the engine is in a car or a plane. Near me, it's the other way around. I could go over to like Sonoma Raceway and pick up ethanol-free gasoline if I wanted. Yeah. Anyway, interestingly, there is actually also something called UL91, which is pretty much the same as pump gas, unleaded, unethanoled, but it's backed by a standards document, and it was rushed through approval in the US because the Department of Defense wanted a standardized fuel to power drones that were powered by Rotax engines. But between the standard being created and launched, the priorities changed, and it's not being made by anyone, even though it exists as like an accepted standard of fuel. It would be great to have this kind of stuff at every airfield and solve like 90% of the problem. Except most airfields can't afford to carry more than one fuel for piston engines, so they choose the one that works with 100% of aircraft rather than the 60%, which means that even the people with aircraft that don't need those high octane fuels are largely forced to use the stuff with the lead in them. And that is a problem, because lead causes problems which mean more maintenance, right? The lead actually leads to lead deposits that can foul spark plugs. And the fact that modern synthetic motor oil really doesn't like lead means that the average plane has to have its engine serviced about twice as much as it would if it was running on unleaded fuel. So those 60% of pilots are being forced to do more maintenance on their aircraft because of the lack of an unleaded fuel. Okay, so if not lead, what could be used? Well, it turns out there are actually a bunch of chemicals we've talked about that can act as octane boosters. There are things like aromatic hydrocarbons, benzene, toluene, xylene. There's alcohols, ethers, and a handful of alternative metal organic molecules that replace the lead with something else, such as ferrocene or methylcyclopentadienyl manganese tricarbonyl, which is better known as MMT, because who wants to say that? Many of these have compatibility problems, interacting poorly with the engine or fuel system, which makes it a more complicated problem than simply mixing up a batch of something with the highest octane hydrocarbons that you can mass produce. So for unleaded aviation fuels, we have one example that's been in use for a few years. A company called Swift makes something called UL94 unleaded. It's been involved in some extensive tests that, like the University of North Dakota, famously switched their flight training department over, which uses a bunch of like Piper Archers and Seminoles. And they were doing a trial there for a while. They had something like 42,000 hours when they cancelled it because they found valve seat recession. That is, when the valves in the engine close, they back into these valve seats and they're supposed to seal. But it was seen that on some of the planes, the valve seats were getting worn down in a handful of cases. And that meant the valves were no longer sealing and they were losing compression. That is a problem that gets constantly talked about. It was seen in car engines in the 80s during the unleaded transition. And there are people who theorized that the lead in the fuel forms like soft oxides that float around and they cushion the valve's impact as they close, and this protects the engine. And then there are the chemists who point out that because lead oxides are bad, the 100 low lead fuel contains ethylene dibromide, which is a lead scavenger. It's an additive designed to soak up any lead and turn it into a more volatile lead bromide, which condenses at a lower temperature and enables it to remain in a gas so it's blown out of the engine. But if it does form into a solid, it's a salt which is harder than lead oxide, so it's more likely to act like a sandpaper, so it's unlikely to help soften valve closing impacts. The chemists I talk about the valve recession issue believe that it's more about the reduced octane rating as they transitioned, and it changes the combustion properties. Regardless, hardened valve seals are used in modern engines, and it seems like a good idea in general for all the engines to start using these things. The UND test, the engine manufacturers blamed the fuel, while Swift, the maker of the fuel, said that the mixture selection was running too close to peak exhaust temperature, and pilots using this new fuel need to adjust their technique when they're adjusting their mixture ratio, right? Meanwhile, by the way, there's another flight school in San Carlos near me, and that's been using the 94 unleaded for 10,000 hours, and they haven't had the same problem. Both MOGAS and UL94, they currently require the aircraft to go through a certification process if the pilot or owner wants to use it. A mechanic has to do some basic checks to make sure that the aircraft is approved for this fuel, and then he'll sign off on a document that's called a supplemental type certificate, which may include some extra stickers for the plane confirming that it's actually okay to use this non-standard unleaded fuel. This may seem like some dull paperwork, but it's actually critically important to understand what happened next and what happened with the FAA. Because over the last few decades, the FAA has in fact been working on and off on an unleaded aviation fuel that can work for all the planes. And they did this through a program called PAFI, the Piston Aviation Fuels Initiative. And then later there was one called EAGLE, Eliminating Aviation Gas Lead Emissions. And these haven't been particularly successful, partly because the first time that they launched this, the criteria for success were so narrow that the only thing that could possibly win was existing 100 low lead fuel. More recently, the criteria have been loosened up, but they are still sort of skewed to favor existing refiners because, working with something as toxic as tetraethyl lead means that the people who make leaded avgas have the market more or less sewn up since it's hard for anyone else to come in and compete with their own formulation. So a handful of companies have worked within these programs to try and develop a drop-in replacement, right? There was Shell Global Solutions, not to be confused with Shell. There's Phillips, Afton, LyondellBasell, and VP Racing. And at this point, the only one that hasn't given up, failed, or dropped out has been the LyondellBasell VP Racing team. And earlier in this year, the CEO at an aviation, I think it was at Oshkosh, they stated that they don't actually think that a 100 octane aviation fuel is possible within the FAA's rules. They're close. They have a fuel that has 20% ethyl tertiary butyl ether, or ETBE. That gets 100 motor octane number, but to satisfy the FAA, they need to get that up to 104. And the only thing that they could think of and try was to add manganese in the form of MMT. And Phillips, by the way, had also tried that, but the manganese deposits left in the cylinders were a problem, and that forced them to drop out of the competition. There is a third party, however, who has got a functional drop-in replacement, a company called General Aviation Modifications Inc. And it's run by the ultimate aviation engine nerd, George Braley. He's been running engines on his test rigs with his formula for years. In fact, most of these fuels that I've talked about have been run on his engine test cell in the past because his system is considered to be one of the best in the world. Now, he didn't join PAFI, he didn't join Eagle Processes because in part, none of the work that he'd done prior to this would have counted towards that, and he'd have to do it all again. He also said he had issues with protecting his intellectual property from competitors. So instead, he got the fuel approved via a supplemental type certificate, an STC. And it's actually now approved for pretty much every piston engine in the US. Well, at least everyone that works on a fixed wing aircraft. They're still working on helicopters. But that was over a year ago. This approval process, by the way, was a drama in itself, with people at the FAA sometimes trying to push it, while others were pushing back against it to slow it down. In the end, he succeeded. So great, we've got the solution. And that's what has gone on sale in California recently. But because it's approved as an STC, that means that each individual aircraft has to get approval with a mechanic signing off and paying a couple of $100s to GAMI for administrative costs and, more or less to compensate George for his work on this. That means, however, if you don't have the certificate and you land at an airfield expecting to fuel up, you might be unable to do so until you go through the STC process, which requires a mechanic on site, even although there's no actual changes needed for the fuel system. Now, the exact details of what chemistry is involved is beyond me, but looking at the patents and other public data suggests that GAMI's G100UL is about 15% isopentane, 50% isooctane aviation alkylates, and 30% xylenes, and 5% aromatic amine octane additive, which, xylenes, by the way, those are xylenes are basically dimethylbenzene, right? So it's a benzene ring with two methyl groups hanging off the side. And there's like 3 different versions of this because they can appear in different locations. Aromatic amines are benzene rings again, with 1 or more of the hydrogen atoms replaced by nitrogen and 2 hydrogens. So that's like an ammonia group, right? Aromatic hydrocarbons in general, by the way, refer to molecules with a benzene ring at the core, and there's a long history of these being used as octane boosters. Toluene, right? Monomethylbenzene. And in the early case of like unleaded fuel in cars, there was a class of additives known as BTEX. Benzene, toluene, ethylbenzene, and xylene, which they eventually abandoned because benzene's actually pretty toxic and carcinogenic. In fact, all of these things are. Anyway, GAMI's fuel is, interestingly, a little denser than existing fuels, but it has comparable energy density. So this does mean that if you fully fuel a plane with this unleaded fuel, it will be slightly heavier. So you need to, be careful with your weight and balance. But it also means you can get slightly longer range because you've got more energy in it. For the last year or so, it's been demonstrated on a twin-engine Baron, with one engine using traditional 100 low lead and the other using a G100UL. And the aircraft performed just fine. The main observation that they had is that, by the way, this stuff smells a bit different. It smells a lot like turpentine. It has a habit of attacking paints that were traditionally unfazed by 100 low lead. And in the last few days, there's also been some postings showing that it's affecting nitrile O-rings. It causes them to expand, which could be a problem with some sealing systems. So it's recommended that those will be replaced with silicone or fluoroelastomer equivalents. So there might have to be some replacement parts, but it's not nearly as complicated as, say, having to add electronic ignition timing to every engine that's out there. In fact, repainting the plane with new, fuel-resistant paintwork might be more expensive compared to any of the mechanical changes that might be needed for G100UL. Regardless, this looks like the best option out there, except that the engine manufacturers issued a notice earlier this year saying that they won't honor warranty of engines that are converted to run on the stuff or they may not honour it, right? Even though the FAA says this fuel is fine, aircraft owners might find themselves having to prove that the unleaded fuel wasn't a problem if something goes wrong with the engine, if they want the manufacturer to cover any manufacturing defect that would have otherwise been covered under warranty. Another important factor is that any new fuel has to be fully fungible with existing fuels. That means if you mix a new fuel with existing 100 low lead, then in any proportion, then it should operate correctly, providing 100 octane or more. And it should do that in all engines. And of course, the new fuels need to be tolerated by the entire fuel system, right? Again, they can't attack components such as those O-rings. And this is where things become problematic because, as I understand it, Game's fuel works fine when mixed with 100 low lead, but it's not supposed to be mixed with fuels containing alcohol, so that ruins my plane, right? Uh, Similarly, Game's fuel doesn't believe that it's going to be fungible with the ether-based fuel that's coming from Leondale Basel, VP Racing, and that's going to get fleet approval, hopefully. There's also another 100R fuel. It's from Swift, and that has to be approved via STC as well, but it's now available for thousands of aircraft. But it too uses ETBE and is likely non-fungible with Game's fuel. So there is a hypothetical near future where fields switch over to lead-free fuels because of local rules, but the aircraft arriving from elsewhere may not be able to fill up because they don't have the appropriate certificates, or they've been using another type of unleaded fuel which is not fungible with the type at that field. Remember, most airfields can't carry multiple fuel types. It's just too expensive to install all those extra tanks and get them approved for what is a relatively niche market. So we've got to the point where the FAA's program hasn't really delivered a solution, but it may soon. There's at least one viable version from outside the program, which has an approval process that limits its use to people that are going to go through the STC. And there's a lot of people out there who would really like to do the right thing and get the lead out of aviation fuel so that they can cut back on their maintenance, so that they can cut back and start using synthetic motor oil, and so that they're not poisoning the communities around them. And remember, this isn't just a US problem, this is a worldwide problem. There are planes around the world that are still using this stuff, and there are unleaded alternatives elsewhere that are available in limited quantities. And personally, I wish I had the kind of money that would let me fly a turbine aircraft instead. I'm Scott Manley. Fly safe.